Hi everyone. In the last few classes, we have discussed the spectral theorem for self-adjoint operators, both the versions, the integral form as well as the multiplication form. For normal operators also, we have discussed the spectral theorem, which is a multiplication form. Next, we want to discuss the spectral theorem for normal operators, which is the integral form. To do that, we need the definition of spectral measure. So today we are going to discuss about the definition of the spectral measure and a few examples and one or two important properties of spectral measure. First of all, let us start with the definition of a spectral measure. So let us start with the definition. Let x omega mu be a measure space and h be a Hilbert space. A spectral measure for the triple x, omega and h is a map E from omega into B of h, which satisfies the following condition. Following conditions. The first one, E omega or E delta is an orthogonal projection for each delta in omega. The second condition is E of empty set is 0 and E of the full set is identity. The third condition is E of delta 1 intersection delta 2 is nothing but E of delta 1 multiplied by E of delta 2 for each pair of sets delta 1 delta 2 in omega. And the fourth condition is if delta j be a sequence of pairwise disjoint sets from omega, then E of union delta n must be equal to summation n equal to 1 to infinity E of delta n. Okay, so now we have to mention what is the in what topology the series on the right hand side of this equation converge. So we can easily show that this is a convergence in the strong operator topology of B of h, or it's a pointwise convergence. So that follows from the point 3. So let us write as a remark. So let us say this is star. So if you look at by 3, if we take delta 1 intersection delta 2 be empty, then we can conclude that E delta 1 multiplied by E delta 2, that is E of delta 1 intersection delta 2, and this is E of phi, that is 0 by condition 2. That means we can conclude that E delta 1 and E delta 2 are mutually orthogonal. Okay, that means if you look at the equation star, the convergence on the right hand side of star is nothing but convergence in the strong operator topology. Hence, E union of delta n equal to 1 to infinity of x is nothing but summation n equal to 1 to infinity E of delta nx for every x in H. This is a convergence in the strong operator topology of B of H. So let us look at a few examples. For the spectral measures, let us look at let us take x omega mu be a measure space and h to be L2 of mu. Now define E of delta to be the multiplication operator induced by the characteristic function induced by delta for all delta in omega. Then we can easily show that E defines a spectral measure for x, omega and h. Let us look at one more example. So let us take x to be the set of all natural numbers and omega to be the power set of n. And mu is the counting measure. Now if delta in omega, so define E omega to be the diagonal operator with diagonal entries as alpha 1, alpha 2, alpha 3, so on, where this alpha j equals to 1 if j is delta, 0 if j is not in delta. For example, if you take if delta to be 1, 2, 3, then we can say that E delta is nothing but the diagonal operator with diagonal entries as 1, 1, 1 and remaining 0. If delta to be, for example, if we take 1, 2, 5, 7, then we can say that E delta is nothing but is the diagonal operator with the diagonal entries having positions at 1 to 5 positions to be 1, remaining places 0, that is 1, 1, 0, 0, 1, 0, 1, all remaining entries to be 0. This is an orthogonal projection and to span E1, E2, E5, E7 where E's are the standard orthogonal basis for L2. Okay, so we can slightly generalize this one. Let us take x omega mu be a measure space and let us take phi to be L infinity of mu. Then we can define E of delta to be multiplication operator induced by the characteristic function of phi inverse of delta, where delta is coming from omega. You can easily check that E is a spectral measure for x, omega and L2 of mu. E is a spectral measure for x, omega and L2 of mu. Okay. Suppose we have one spectral measure. From that we can also generate one more spectral measure by changing the Hilbert space. Let us look at that example. Let E be a spectral measure for x, omega and h. Let us take K to be another Hilbert space, and W to be a unitary map from H to K. That means it is isometry and onto. In fact, it is also linear. Then define another spectral measure f of delta to be W E delta into W inverse. Now this is again a map from K to K. So f delta is a map from K to K. So that means f is a map from omega into B of K. Earlier E is a map from omega into B of H. So this is a spectral measure for x, omega and K. Okay, that means we can actually generate spectral measures using the existing spectral measures. Okay, so these are the few examples of spectral measures. Let us look at some important properties of spectral measures. Let us write a theorem. Let E be a spectral measure for x, omega, h. Let us fix two elements g and x, g and h in h, and define E of gh to be a map from omega into C by EGH at delta is nothing but inner product E of delta acting on G with H. So for every delta in omega. Then we can show that this E suffix GH is a complex measure. EGH is a complex measure with total variation at most norm G into norm H. Okay. So that means given a spectral measure, we can actually create a complex measure out of that, depending on by fixing two vectors from the Hilbert space. If you change the vectors, then the measure also will change. You will get a different complex measure. So let us look at the proof of this result. Now when we fix G and H in the Hilbert space H, inner product E delta at G with H is a complex number. Now using the fact that E is a spectral measure, we can show that E suffix GH is a complex measure. Now only thing we want to show is that its total variation of E suffix GH is at most norm G into norm H. So let us look at a partition. Let delta 1, delta 2, so on, delta n be a partition of X. That means these sets are disjoint and their union is X. So let us write mu as E suffix GH. We want to look at summation k equal to 1 to n modulus of mu of delta k. We want to show this is less than or equal to norm G into norm H. So this is nothing but summation k equal to 1 to n. This is modulus inner product E of delta k acting on G inner product with H. Okay, so let us call this as equation 1. Now since inner product E delta k acting on G with H is a complex number, we can always choose complex numbers alpha j. Choose alpha j in C with mod alpha j equal to 1 for j equal to 1 to so on n, such that modulus E delta j acting on G inner product with H is nothing but alpha j times inner product E delta j acting on G inner product with H. So we can write 1 as summation k equal to 1 to n mu of delta k. So this is nothing but summation k equal to 1 to n. So this we can write as alpha k inner product E delta k acting on G with H. Okay, now this is less than or equal to norm of summation k equal to 1 to n alpha k E of delta k G into norm H. Now if you are able to show that this part is less than or equal to norm G, then we are done. Okay, so next consider norm of summation k equal to 1 to n alpha k E of delta k G square. Now we know that since delta k's are disjoint, so E delta k's are orthogonal projections, hence we can say that alpha k into E delta k G, they are orthogonal vectors. So this can be written as summation k equal to 1 to n mod alpha k square, that is 1. So this is norm of E of delta k G norm square, and this is nothing but E of union delta k acting on G, this is norm square. This is k equal to 1 to n. So this is nothing but norm of E of x G square, and we know that E of x is identity, hence this is norm of G square. That means the norm of the left hand side summation k equal to 1 to n alpha k E delta k G less than or equal to norm G. Hence if you look at this as inequality 2. So by inequality 2 and let us say this is 3, we can conclude that 2 and 3 we get summation k equal to 1 to n mu mod of mu delta k is less than or equal to norm g into norm h. This completes the proof of the theorem. Okay. So this is one of the important property where we can actually associate a complex measure with a given spectral measure. Now we want to integrate a given function with respect to the spectral measure. So for that we use this fact, that means this complex measure we can use, and using that we can actually integrate a given bounded measurable function. So let us fix g and h in h, and we have defined EGH acting on delta. This is inner product E of delta G with H. Okay. Now if you want, now we know that E suffix gh is a complex measure, hence so we can integrate a given function with respect to this complex measure. Suppose phi from x to c be a bounded measurable function, then we can actually define integral over phi dEgh with respect to this complex measure. So for example, if you take phi to be the characteristic function onto a measurable set delta, then we can get that integration over x with respect to this measure d of EGH. This is nothing but integral over x chi of delta dEgh, and this is nothing but E of GH acting on delta, and this is nothing but E of delta GH. Okay, now if you take any finite linear combination of such characteristic functions also, we can define the integration. Okay, now using this observation we want to define an operator. In fact, we want to define what is the meaning of such a thing. So we want to actually, using this, we want to show that we want to give a meaning for integral phi d of E. So what is the meaning of this? Okay, so we will write this as a theorem. Let E be a spectral measure for x, omega and h, and phi be a bounded measurable function from x to c. Be a bounded measurable function then there exists a unique bounded operator A on H with the following property. The property is that if epsilon is positive and delta 1, delta 2, so on, delta n is a partition of of x with the property that supreme of mod phi x phi y, where x and y are coming from delta k, this is less than epsilon, where k equal to 1 to so on n. Then for any choice of xk in delta k, where k equal to 1 to so on n, so we have that norm of a minus summation k equal to 1 to n phi of xk into e of delta k is less than epsilon. That means this bounded operator a can be approximated by the operator summation k equal to 1 to n y of xk e of delta k. Okay. So to prove this result, we want to show that there exists a bounded operator a having all these properties. That means a can be approximated by the operators of the form summation k equal to 1 to n phi of xk e of delta k. So let us fix two vectors g and h in h and define b from h cross h into c by b of g comma h is integration over x phi d of gh. We know that e of gh is a complex measure when we fix g and h. Okay. Let us look at the earlier theorem. So we have shown that EGH at delta, that is inner product E delta acting on G with inner product H, this is a complex measure. Now if you look at the inner product on the right hand side, when delta is fixed, we can easily show that this map, since the inner product is linear in the first variable and conjugate linear in the second variable, we can conclude that the map that we have defined B is a sesquilinear map. That means it is linear in the first variable and conjugate linear in the second variable. So we can easily check that clearly this map is a sesquilinear map. And we can easily show that modulus of b of gh, this is less than or equal to integration over x mod phi d of egh. So this is less than or equal to supreme norm of phi into integration over d of mod egh. So this is nothing but norm phi into this is norm g into norm h, because the total variation of the measure EGH is bounded by norm g into norm h. So that means B is bounded sesquilinear map. We know that given any bounded sesquilinear map, there exists a bounded linear operator such that B of gh is inner product of Ag with h. Hence, there exists a unique bounded operator A in B of h such that B of gh is nothing but inner product Ag with h. Let us call as this equation star. So this is true for every g and h in h. Okay. Now what we want to show? We want to show that A satisfies this property. Okay. Now A minus summation k equal to 1 to n phi of xk e delta k is a operator. So we want to show that norm of an operator is less than epsilon. So let us quickly recall that if T is a bounded linear map from H, then we have that norm of T is supremum over modulus inner product T of xy, where x is coming from the unit sphere of H and y is also coming from the unit sphere. Now we can take T to be the difference operator A minus summation k equal to 1 to n phi xk e delta k. So to show that norm of that operator is less than epsilon, it is enough to look at norm of the operator modulus of inner product tx with y, where t is the difference operator that we have here. Okay, so let us fix let h and g is in H and epsilon be fixed. Let us take a partition, let delta 1, delta 2, so on, delta n be a partition of x and xk are coming from delta k equal to 1, 2, so 3, so on n. Now let us consider norm of modulus inner product AGH minus summation k equal to 1 to n phi of xk. Here we have E delta k inner product G with H. So this is E of delta k inner product G with H, modulus of this, because we know that inner product AG with H, if you look at by definition, is integration over phi dgh. So this is modulus integral over x phi dgh. We can write this as phi of x d of g comma h minus summation k equal to 1 to n phi of xk. Okay, so here we want to see what is the value of this one. So we know by the earlier observation E of delta k gh is nothing but integral over x chi delta dgh at x. So we can say that this part we can write as integration over x chi of delta k d of g x modulus. Okay, so this we can write as summation. We can write this summation k equal to 1 to n integration over delta k phi of x d of e g h at x, because delta k forms a partition for x. So this is disjoint, x is nothing but disjoint union of delta k. So we can write this way, minus summation k equal to 1 to n phi of xk into this is integration over delta k d of e g h acting on x. Okay, so we can write this as modulus summation k equal to 1 to n integration over delta k phi x minus phi of xk d of EGH x. Now this is less than or equal to mod phi x minus phi xk less than epsilon, because by the definition supreme of mod phi x minus phi xk in delta k, when x is in delta k, this is less than epsilon. So we can write this is epsilon into summation k equal to 1 to n integration over delta k d of mod EGH acting on x. So this is nothing but epsilon integral over x d of EGH modulus. Now we know that this is less than or equal to norm g into norm x. So this is epsilon norm g into norm h. Okay. Now taking over supremum over norm g equal to 1 and norm h equal to 1. So taking supremum over norm j equal to 1, that equal to norm h. So we get that norm of a minus summation k equal to 1 to n phi of xk e of delta k norm less than epsilon. Okay, so this is what we get. Okay, so in other words, summation k equal to 1 to n phi xk e delta k, so that actually as n going to infinity, that is integral of phi dE. So we can write a as, so we write a as integral phi dE. Okay, or in other words we can write a of gh is integration over x phi of x d of eg of x. Okay, so this gives an operator. Given a spectral measure, we got a boundary linear operator which satisfies this condition. Okay, so we'll stop here. Thank you very much.